Welcome everyone. Let's start with our basic concepts that you need to do lab 2. As we already done with our lab 1 and we know all the important concepts of C. We know how our source code goes into the memory and runs in a CPU. We know about the memory organization a bit and how can we access them. So now we are ready to program our microcontroller because we can use our C language to program our microcontroller to give it a specific tasks to solve, and that's all this lab about. So here we have a picture of our microcontroller that is SiFive FE310. And we are going to use this microcontroller in our lab. It is a RISC-V architecture-based microcontroller. So the CPU is 32-bit RISC-V architecture, and the maximum clock frequency we can achieve from this microcontroller is 320 megahertz. It has also the fastest RAM, SRAM of 16 kilobyte. As we know, SRAM is expensive than the flash memory. And the flash memory is just only 4 megabyte. So the CPU here we have that is 32-bit RISC-V. It is RISC-V based architecture and have almost all kind of peripherals to implement a real system. For example, you can easily build an automated object detection car using this microcontroller. So yeah, I mean, let's start. So for lab 2, I just want to revisit the program execution concept again. We know after compilation of our C program, we get the machine or the binary code, and each line of our machine code represents an instruction, right? So in our memory, you can see here each segment, each segment of memory address contains our instruction. And this is basically in binary, but I just wrote it in assembly format to read it easily. But in memory, this is all binaries. For example, 0, 1, 0, 1, all the way to 32-bit binary number. And we know how it, how the register of a CPU try to access these instructions and, execute these instructions over and over and finish executing our whole program. But do you think we only have the code segments into our memory as it shows in this slide? For example, let's say our code sorts a large, let's say 10,000 elements of array. It just sort that array from maybe ascending to descending order. And if we don't have the different address space, basically that means we have the different segments that can have the different access rights. For example, our code segment is often marked as read-only to prevent accidental overwriting of the executable code. So yeah, I mean, the question is, we have the code, data, all the necessary IO memory, registers and everything. Why don't we have just a unified memory? Why we are we are doing segmentation of this. We are doing segmentation of our memory and keep different data into different segments, right? That's our question. So yeah, as I already told you, our code segments only contain the codes. Our data segments that contains, for example, as I already told, I give you an example of sorting and large array. So that array, is resized in the data segment of our memory. And for example, the code segment is often marked as a read-only to prevent accidental overwriting, because we don't want to, we don't want our program to get suddenly stopped because of, accidental overwriting. But the data segment can be read-write, right? We can read the data from the memory region, and we can also update the data in our memory region. So you see here we have different accessing, we have different accessing permission of this memory. We have different accessing permissions of this of the data of these different segments in our memory. Also, it is very easier for operating systems and compilers to manage memory when it is divided into segments with specific roles. For example, for operating system, when it linking the different object files, for operating system, it is easier if it knows like where to relocate or locate the codes into the memory. And last but not least, if we need the dynamic memory allocation, for the dynamic memory allocation, we don't know the exact size of our data, and if our memory is not if our memory is unified, not divided into different segments, we might accidentally overwrite different region of the code. So that's very dangerous, right? Yeah. So in summary, the main memory is divided into regions. There is code section, data section, peripheral section, and system section. And we have the I/O, the input-output devices, and the memory mapped I/O allows peripherals to be controlled directly via the CPU's address space. So there is the address space that CPU uses to communicate with the I/O, and this memory locations, in the peripherals, actually are physically present in the I/O devices. In that way, the CPU can control our I/O devices. So here we have the table from our from documentation of this FE310 microcontroller, and you can see here we have different memory addresses, and it has different segments. For example, we have the data memory segment, that is on-chip volatile memory. We have the code memory where we stored our codes. We have the peripherals. We have the peripherals here also. The peripherals means we have all those peripherals registers to to control the I/O devices through the peripherals. And our embedded system is designed to run only one program. And if we want to run another program, we have to program it again, right? So when we program our microcontroller, our code section goes to this code memory, and the data section goes to the data memory. and we have this peripherals to talk with the external devices. Now, for lab 2, we have to understand the the concept of the GPIO, that is general purpose input output. So GPIO is basically 32 general purpose input output pins we have, and those pins can be configured as either inputs or outputs. So uh, why we need these input output pins? That's my question. So the answer is, I mean, these input output pins, we can control them using our CPU, and those pins can help us interacting with a wide range of external components like LEDs, buttons, sensor, etc. So here, in this picture, you can see this microcontroller is connected to a sensor and a LED device, and how these devices are getting powered, right? So these devices are getting powered through these GPIO pins, and we are controlling the pins through our CPU. Now the question is, how can we control these pins? So that is the interesting fact, because each pins can be controlled using a resistor, and that's how these registers have these base addresses. You can see here this GPIO has the address of 0x1001 200. So basically, these pins, these 32 pins have, we can control those 32 pins using the registers that has these memory addresses. Yeah. So as we have 32 pins from GPIO, we have to tell the CPU which pin we want to enable, or are we considering that pin as a input or output? And if we consider that pin as a output, what should be the value of the output, or what we are trying to pass through that output pin, etc., etc. So, so that's why, as I already told you, I mean, those pins are connected with the CPU using some resistors. And these resistors are, as you can see here, we have the base address of those resistors, that is here. And if we add different offset with those base addresses, we can control those resistors value. For example, if we add 0x04 with this base address, we can control we can control we can control any pins input. We can control the input pin using this address. We have also pin output enable, and we have the address of the output value. So they are all connected in the CPU, and in a hardware way, so it can it can pass those data through these pins of GPIO. And this is the top level block diagram, and you can see here this GPIO is connected all the way to our RISC microcontroller here. So yeah, so now let's get to our code. So So for lab 2, you will see we will give you two library files. So these library files have all the necessary informations to connect the GPIO with the CPU and the addresses we need to access and I mean modify the value of those addresses. So in the lib.h file, header file, we have all the definition of base addresses. So this was our manual, and we collect these base addresses and the offsets from this board manual. And we have those register addresses to manipulate the register value. Basically, if we can control those values, we can control the external components that are connected through these GPIO pins. So, and also we have this define, define keyword. So this is a preprocessor directive used to define macros that are replaced by their values before the compilation of the program. So during the compilation, if we have this variable that is, we set by using the define keyword, this variable will get this value during the compilation. So it just one type, but just the typeless. There is no type on define. You can define any value, on any variable using this define. Now let's go through our next file that is ESS310_lib.c. So this lib.c file contains all the helper functions that reads the current state of the GPIO, sets the bit corresponding to the GPIO pin. For example, we can making it as an output or as an input, and we can also write the updated value back to the register. So let's go step by step. So our first function in this lib.c file is GPIO mode. This is a void function, and we have two arguments for this function. That is, it takes GPIO, the pin number, and the mode. Both are integer value. The mode can be 1 or 0, and the pin number, we have different pin numbers. For example, here in lab 2, our goal is to turn on some LEDs on our board. And to turn on those LEDs, we have to use these values. This is already predefined by the board. You can get these numbers from the documentation. These LEDs are default LEDs from the board. If you want to use any external LED, you can use that. So basically, these pins are connected to the LEDs of the board, and through this pin, we can give, for example, 5 volts to turn on the LED, or 0 volt to turn off the LED. So here, so here the mode is basically on and off argument. And we have initialized a 32-bit uint, that means unsigned. That means the number is positive, must be positive, and it's a 32-bit unsigned integer number. And the name of the variable is val. Next, what we are doing based on the mode, this output is defined in the lib.h function. As you can see here, the output value is 1. That means if mode equal to 1, that means if it is true, we'll go through the next line of this codes because the condition is met. So if mode is 1, then what we are doing here? So we have this line, the long line. So it's basically consists of some pointers, a keyword that is volatile, another keyword uint 32 underscore t, then some variables. So these variables, GPIO underscore control underscore address plus GPIO underscore output underscore enable is basically the memory address of the register of output underscore enable. How? We know this control underscore address is basically the base address. Here you can see we are adding the output underscore enable, that is here output underscore enable, that is 0x08. So we are adding 0x08 with this base address to try to modify the value of this pin output enable register. So we are trying to enabling the output pin. So how can we enable them? So yeah. So also what we are doing here, we are this part is the memory address, and we are casting them using this keyword volatile uint 32t. So this casting here is telling that the compiler to treat the numerical value resulting from this address as a pointer to a volatile 32-bit unsigned integer. So whatever value we are getting from this memory address, as we are using a pointer sign here, that means we are dereferencing this memory address. We are getting the value from this memory address, and that value we are casting it a unint 32t volatile variable. So this value is basically because as we declared the val as a 32-bit unsigned variable, so we want to convert whatever we're getting from this memory location also as a 32-bit number. And the number here is we are using the volatile term here because we know during executing of this program, the value of this address can change anytime. So that's why we are letting the compiler know the value can change anytime, and you don't have to think about that. So that's why we are using the volatile keyword here, and we are storing whatever value we have inside of this register into the val variable. Now after that, we are doing some operation here. So this operation is nothing but we are getting the register value and we are storing it to the val variable, and we are whatever value we have inside the val, we are doing some operation. So what operation we are doing? This is a very specific operation for turning on the LED. So what we are doing here, we have the GPIO value. So for example, if we want to turn on the red LED, we know the value is 22. So we are shifting 22 times on the left hand side. So here 1 left shift 22 is basically this binary value. And if you convert this binary to hex, you will get 0x40000. And then this OR sign here, this OR sign is what it is doing here. After shifting this value, we are ORing with whatever value we have currently in the val variable. So in val variable, we have the register value of this address. And for example, let's say that is 000011 and all the way to 0. And we're doing OR operation. So this sign equal means we are doing bitwise OR operation. So in the bitwise of OR operation, if there is 1, we will get 1. If it is 0, it will just follow whatever value have the the left hand side, variable. So we are doing we did the OR operation. You can see here, as most of them are zero, it's zero, and this 1 and 0. If we do OR, 1 0 means 1, and we get this final value. And in hex, that is 4300. Now, again, this number, the shift operation 22 times is specific for that specific LED, and this is already predefined. Now, the next line, what we are doing, you can see here now our left-hand side is this memory address of this output enable. So we are writing, or we are modifying the register value of output enable with our new val variable. So we are rewriting, we are writing the value to this register, this address. So write to this address directly with the value val. And now whatever value we had previously, it now changed, right? So yeah, so that's how our function is working. So now in high level, to turning on the LED in our microcontroller, what we are doing, this is our flowchart. So first, we are enabling the output enable register. We already saw how we can enable the output enable register. So then for a specific pin, then what we're doing, we are again, we are making active high for the output. So basically we are setting the value in this output XOR register. We are making it active high. And if you follow the code, you will see how we made the active high for this output register. Then if we able to succeed on that, the output pin is high, then we have to set this register value output GPIO output val to on or off value. So if we able to do if we want to write on or on value on this register GPIO output val, then we'll see we turn on the LED by this specific color. And after turning on the LED, if we want to change the LED color, we can add some delay, and then we can turn off by again changing this output val to off value. Or if we want to change the LED color, we can go back to our very first stage. So here we have 3 LEDs, right? Red, green, and blue. So what we have to do for red, green, and blue, we have to manually, we have to enable for each, we have to enable this output enable register. We have to enable for all of the speeds if we want to turn on the LEDs for red, green, and blue. If you just only enable the LED for red, but you change the output value for green, so it will not work. So that's why the question is, did I already enable and make output pin high for my LED color? So if you want to change the color from, for example, red to green, you have to first enable the output. You have to enable for that specific pin. For example, green, you have to use GPIO value 19. For blue, it's 21. So you have to enable that for a specific pin, and do the rest of the things again. So yeah, so this is in high level the flowchart, how you can turn on the LED. So that was all for lab 2, but I want you to show some way we can observe this register's value in our Visual Studio Code. So let's say, let's open my Visual Studio Code. So here you can see here in Visual Studio, I have opened my lab 2. We have all those source files. This is lib.c, and we have lib.h file. So as I already discussed with you, like how this operation is happening here. So now let's say I want to observe the register's value. How can we do that? So we have a debugger option here. If we go to run, start debugging, you can observe the register's value from your from your microcontroller directly here. So for that, you have to must connect your hardware with your computer, and then go to the run and start debugging. So after if you are in the debug mode, you will observe the color of this bar change from blue to orange. And you will be in this section of your Visual Studio, that is run and debug, and you will have this tiny controller to go through the code. So yeah, so for the very first time, you will only observe, for example, the local variables here. So you can now you can now skip what you have here. But in the below, we have all the, you can see all the memory segments from our CPU address space. We have peripherals, we have the registers, we have the memory. So as we know, we are dealing with the peripherals. If we click on it, we will see all the peripherals from our microcontroller. So currently we are using the general purpose input output controller, GPIO. So if we expand this section, we will see all the registers. For example, if we add 0xc with our base register, we have the register of output value, right? So you can see here 0x0c is basically our register for output value. So now you can see here, here we have the port, and I converted, I changed the value format to binary, but you can change it to again hex. So if you have hex format, you can just click on it and right click on it and set the value format. You can click on the binary to observe the binary values. So as we know, all the registers are 32 bits. If we count 1, 2, 3, 4, 5, 6, 7, 8, we have total 8 segments with 4 bits. So 8 into 4, total 32 bits. We have the output enable, the input enable, all the registers we saw. So now let's yeah. So yeah. So just for reference, we have Yeah, we have those registers, output enable, and let's see how each operation is happening inside of the code. So here, how we have our main functions where we, we have a task to turn on the LED. So let's go through a step by step inside the code. So we know our C code starts inside of our main function. So that's why when we start our debugging, you can see here the marker is here. And I set some breakpoint inside our library. So these breakpoints, you can see it, if you just click here, you will create a breakpoint. So let's say I created a breakpoint here. That is, I want to directly jump here when running my code. So how can I jump here? We have this little control bar. You can see here, this is a step over, this is a step into, and this is a step out. So if we click on the step over, now I'm currently in my bling.c file, and I want to directly jump to this libc.file, because in my underscore bling.c in my main function of this bling.c file, we already call this function multiple times. So I just want to jump on this line and try to observe whatever value we are getting inside this val variable, and how we are rewriting the registers using this line. So let's click on here. So you can see the initially all the values are 0. For example, the output enable is 0. The output value is 0 because we are not setting anything yet. And yeah, so let's try to jump step over. Yeah. So now we are here, and you can see here we have the local variables we created well. So now we have nothing here, nothing inside of the val variable, and all the values are 0 as well. Let's say now we are connecting this line, and let's click to the step into, because now we want to execute line by line and observe the value. So now currently we are in this line. So if we click on the step into, you see this line, our VS Code executes this line, and you see now the value is having value 0. So because this value, let's try to observe the hex value. You can change this local variable's value from decimal to hex using this command set output radix 16. So you can see here it changed to hex. And so why the val is having value 0x0? Because this register output enable is 0. That's why the value is getting 0. Now for our turning on the LED, we have to set some value using this operation. So let's step into. Now you can see here the val has the value 0x40000, and now we want to write the register with this value. So now if we click this step into, you will see this output enable is changed, right? It should get this value as we are executing this line. You see the value is changed from 0 to 1, because this 0x400 is basically, if we convert this binary to if we convert this hex to binary, you will get this value. So now you see we rewrite the register. Now we are let's execute the next line. So first, as I already told you in our flowchart, first we enable for a specific pin, we rewrite the register output enable for our specific pin. Next, we will rewrite a register GPIO underscore output XOR to make it active high. So let's see how we can do that. So you can see here inside our code here, we are based on the LED number, we are rewriting the value inside this register, that is output XOR. And the output XOR is here. Now it's having all the zeros value. So let's run it. You see, the output XOR is also changed from 00 to all the 08 to this 0100. So now, you can observe how we are rewriting these values and in the register, and I mean, uh, trying to rewriting these values, we can turn on the LEDs. So in our next part of the code, we are going to use this GPIO write. I don't want to go through this part now because then I have to show you the solution, and I don't want to do that. So in the GPIO write, this GPIO output val, that is this port, you will observe after going through these lines of code, you change the value of this register, right? And by doing that, you can turn on the LED light. As I told you, if you finally change the output val to on and off, you will see your LEDs blinking. So yeah, that was all for lab 2, and we'll go through lab 3 in the next week. Thank you.